Alright, so here's the question I kind of posed to you guys at the end of the last lesson dealing with this stoplight suspended by two cables that are at angles to the horizontal, not vertical cables. So the very first trick to start on this problem is to draw the free body diagram for this stoplight. And if you draw the free body diagram, I'm going to call cable 1 the one on the left, cable 2 the one on the right. We have three forces. One is the weight of the stoplight, which is just its mass times the acceleration of gravity. The second is the tension on the cable on the left, which I'm going to call T1, and the third is the tension on the cable on the right, which I'm going to call T2. Now we're going to run into a very specific problem at this point. Unlike the previous problem where all the forces went either up or down, what I would call a two-dimensional or a one-dimensional problem, and either goes in the positive direction or the negative direction, I now have a problem where the forces act in two dimensions. They can either go up and down, or right and left, or act up and to the right, as in the case of T2, or up and to the left, as in the case of T1. So I'm going to need to break up these forces into their components, the x component being the horizontal component and the y component being the vertical component. So when I apply Newton's first law, because the stoplight isn't moving, I know that the sum of forces in the x direction, if I add up all the forces acting horizontally, I should get 0. And if I add up all the forces or all the components of forces acting vertically, I should get 0. So I'm going to end up with two equations in this particular problem. One in the horizontal world or realm, and the other one in the vertical world or realm. Now, I'm going to pick x to be, or positive x to be the right and positive y to be up. I could technically choose any xy axis I want. It doesn't really matter as long as x and y are perpendicular to one another. In this problem, I just think it makes sense to go with your normal xy axis. So what this means is that the forces acting in the x direction, we have a component of T2 in the x direction, which I can call T2x, component of T1 in the x direction, which I'm going to call T1x, and those two add up to be 0. I have components of both T1 and T2 in the y direction, which I'm going to call T2y and T1y, and then I have weight, which acts downward in the y direction, so those all add up to be 0. Now, if I break up T1 and T2 into their components, it looks like T1x, if I draw this out, is going to be whatever T1 is times the cosine of 35 degrees. T2x is going to be whatever T2 is times the cosine of 43 degrees. And T2y is going to be T2 sine of 43, this side of that right triangle. And T1y is going to be T1 sine of 35, this side of that right triangle. It might help in this problem if you wanted to draw out those right triangles and actually identify what those forces are. So what I've ended up with now is two equations with ultimately two unknowns, T2 and T1. So here's my two equations, the x equation and the y equation. So this is a system of equations problem, very similar to what we looked at with our projectile motion. The trick to doing a system of equations problem is to solve one equation for an unknown and substitute it into the other one. The one that's easiest to solve for an unknown is the one on the left. So I'm going to add T1 cosine of 35, and then I divided everything by the cosine of 43, just solved it out for T2. What I can then do with this T2 is take and substitute it in for T2 in the y equation. What I'm going to be left with now is an equation that only has one unknown, T1. Everything else in this problem is known. We know the mass of the stoplight, we know the acceleration of gravity, 9.8, and all the rest of these sines and cosines are really just numbers. So if I go to solve this equation, add mg, factor out the T1, and so what I ultimately get is mg is equal to T1 times what will ultimately be some number. So here's where I'm at now with my system of equations. I actually went ahead and calculated this number out, and if you do the sine of 35 times the sine of 43 divided by cosine of 43 plus the sine of 35, you get 1.337, which means T1 is equal to mg divided by 1.337. I can plug in m and g that I knew from the beginning of the problem, and I get that T1 is 366 newtons. Now if I take and substitute T1 back into the equation up there, I can calculate T2 is 410 newtons. Now it's worth pointing out at this point that neither T1 nor T2 equals the weight of the stoplight and that T1 and T2 do not add up to be the weight of the stoplight. So if we go back to our original three questions, are the tensions in the cable the same? No, they're not. If not, which one is larger? The one on the left, the one that's more horizontal, tends to have a larger tension. And do the tensions add up to equal the weight of the stoplight? Well, their magnitudes don't. No. The y components would. So what this would mean is that the weight of the stoplight is more supported by one of these cables than the other one. So let's go to another kind of similar problem dealing with 2 dimensions and Newton's first law. Here I have a 10 kilogram block that sits at a ramp angled at 30 degrees. Find the magnitude of the frictional force and the normal force acting on the block. So if I draw the free body diagram, we have weight acting down, friction acting up, and normal force acting up and to the left, perpendicular to the surface. So those are really our 3 forces acting on the block. I know that sum of F in the x direction is 0 and sum of F in the y direction is 0, that I have 2 dimensions. And I could choose the vertical to be y and the horizontal to be x, but then I have 2 vectors that I have to break up into components. I'm going to end up with a problem that's very similar to the problem we just did. But there is a neat trick with this particular problem or this particular situation. And that neat trick is that if friction acts up the ramp and normal force is perpendicular to the ramp, these 2 forces are perpendicular to one another. So instead of drawing my xy coordinate system like that, it might actually be better to draw it like this, where x points up the ramp and y points perpendicular to the ramp. The reason for this is that when I go to write out which vectors in which direction, friction, one of my unknowns, acts entirely in the x direction, and normal force, my other unknown, acts entirely in the y direction. So I have friction minus now the x component of weight equals 0, and normal force minus the y component of weight equals 0. So to figure out what these components are, we're going to fill in a triangle here. Here's the y component of weight and the x component of weight. Again, y component with the perpendicular. Now, if the angle of the ramp is 30 degrees, this angle is also 30 degrees. And we can actually show that here if we were to pull all this over here. If we draw that line in the weight, that angle is 60, which would mean that the angle with that in perpendicular must be 30. So what this would mean is that Wx would be equal to mg sine of 30, Wy mg cosine of 30. So we're left with now is 2 equations, 2 unknowns, and each one of those equations can be directly solved for an unknown without doing any substitution. Frictional force is equal to mg sine of 30, normal force is equal to mg cosine of 30. And so if I work those out, m times g, we get 490 and, oh, excuse me, should be 49 and 84.9, I believe, not 490, 849. So a little mistake here, should be 49.0 and 84.9. 10 times 9.8 is 98, not 980. So there we go, we got our 2 forces, and we got our magnitudes, and we know our directions. So kind of a general strategy for solving equilibrium problems, the very first step that you should do is set up a free body diagram. Hopefully your free body diagram says that everything acts in either a positive, negative direction, a one-dimensional problem. If it doesn't, choose an x and y axis that are appropriate to the problem. If you don't know what's appropriate to the problem, it's, well, perfectly acceptable to choose horizontal as x and vertical as y. That will work for any type of problem. For some types of problems like the block on the ramp problem, your solution may be a little bit trickier, doing our horizontal for x and vertical for y than picking some other coordinate system. Set up your equations for Newton's first law, figure out what forces act in the x and y, set them equal to 0, do some algebra, and then calculate the answer. So that's kind of our overview of equilibrium problems and how to do those types of problems.